Okay. Good afternoon, everyone. Thanks the president for the introduction. We thank the ACP organization work. My name is Xiang Liu, and I'm from Southeast University and Pupil Mountain Laboratories, China. It's my honor to share my work. I will talk about artificial neural networks, assisted geometric shaping optimization, including grid-like mapping. My report is divided as follows. First, I will introduce the background and motivation, and I will talk about the geometric shaping, artificial neural networks optimization model, and parameter optimization. Next, I will introduce the performance simulation. Finally, I will give the conclusions. With rapid development of cloud services, 5G wireless backhaul, and other communication scenarios, there occurs an urgent requirement of transmission capacity. The pursuit of capacity approaching modulation formats is under intensive research. Although the shimmy gain increases with constellation size, it is capped at 1.43 dB. The geometric shaping provides lower shaping gains than probabilistic shaping, but the implementation complexity and difficulty are low. Next, many researchers have investigated geometric shaping combined with pairwise optimization and other schemes. However, they cannot include grid-like code and are typically optimized to perform well only on specific channel model and small SNR ranges. In this work, we use a simple yet effective artificial neural networks models to learn geometric constellation over a wide range of SNRs. The performance of geometric shaping artificial neural networks algorithm is analyzed by GMI and constraint condition. It makes no assumption on the channel model and is easily scalable to constellation of higher order and dimension. Uh, Here, this figure is the block diagram of the geometric shaping artificial neural networks optimization model. The model is an unsupervised learning method embedded with two neural networks. The transmitter and the receiver of single neural networks defined as function f and g. At the transmitter, one whole vector are fed into the encoder with the neural networks. The normalization before the channel possesses the power constraint. The output of the encoder are defined as the constellation points. The received symbols are passed through decoded neural networks with trainable parameters. The width of the neural networks can be timely updated to maximizing the GMI while minimizing the loss function. The goal is to maximizing the GMI by optimizing the location of the constellation points, including grid-like mapping. The average of the cross interval over time is then back propagated to optimize the neural network's width. The size of the neural network's number of layers and hidden units are chosen depending on the order of the constellation. Here we show the parameter optimization. The figure 2a shows the relationship of iteration and the mean loss. We can see the convergence of the mean loss is shown for different training sets. A larger training size leads to faster convergence and better final performance. As shown in Figure 2b, it illustrates that it shows similar characteristics by describing their performance at different training sets. Figure 2c shows the neural network's GMI metric is approaching to the Gaussian GMI metric. It verifies the neural network's training with sigmoid activation can serve as an error estimation. The GMI achieved by neural networks is compared to that of the art modulation schemes considering AWGN channels. Training is performed with the SGD. We basically assume that the decoded neural networks has learned a distribution of the channel, which we use as channel within the receiver. Next, we show the performance simulation. Figure 3a, we can see that an example of setting for QAM constellation with GRILAC is shown. We show the results obtained when both the locations and GRILAC mapping of the constellation points are optimized. Other formats can also be extended. It clearly demonstrates that the constellation points optimized by neural networks have lower BR compared with other schemes, as shown in Figure 3b. We can see the conference scheme is PS and pairwise optimization algorithm schemes. We can see the PS and pairwise algorithm schemes can reduce the BR to some extent. The neural networks can outperform the other reference schemes. We can see that the simulation results that the neural networks scheme can obtain up to 0.2 dB training gains, higher than that of conventional setting for QAM, as shown in the inside of Figure 3c. We show the result obtained when both the locations and GRILAC optimization mapping of the constellation points are optimized. Finally, we give the conclusions. In this paper, it introduced the neural networks-based solution to the problem of geometric constellation optimization. Next, the scheme can operate over a wide range of SNRs and is not limited to specific channel model. It is shown that the scheme outperforms unshaped QAM in terms of GMI and nearly reaches capacity on an AWGN channel. Finally, the simulation results shows that it is promising for other channel models. It can left us future research directions. That's all. Thank you. If you have a question, you can contact me in this email. Thanks again.
Okay, thanks. Good. Any question?
Thanks for your talk. I have a question for your methods. In your presentation, you mentioned you don't need a model for training, or you still need a model training this constellation shaping. Do you need the channel model?
We use the AWGN channel.
So the data you're generated by AWGN channel, or you calculate by the AWGN model for the training. So is the data training or the model training?
Data training. Data is generated by one hot vector.
So this means for your future research work, you can just use data without a model, right?
Yes,
Yes. Okay, but my comment is quite about the GMI or ARLR calculation, because in your GMI, you still need to have assumption of your distribution of noise, right? For example, the log likelihood ratio. When you calculate that, you still need a model. Maybe we can discuss later. Yeah. Thank you.
抱歉。I have one question. In figure 3. Figure 3. Next. Okay. Left figure, figure 3A. How to obtain the gray like when you use the neural networks. Second question is, do you use PRBS data or a random function in MATLAB?
Okay, the gray like mapping. The geometric shaping artificial neural networks model is embedded to neural networks with trainable parameters. The width of the networks can be timely updated to maximizing the GMI will minimize the loss function. When it obtains the gray-like mapping, it can minimizing the loss function will max. Pairwise optimization scheme. We compared with the two schemes.